Okay, now for the integration solutions. First one's this one here. Integral of 100 plus an exponential. First of all, you've got a plus, so there's two terms here, and you integrate terms separately. So the integral of the 100 is 100x, and the integral of e to a linear is 1 on a e to the linear. Where I'm getting that from is the help sheet. In the help sheet we have here that the integral of a constant is equal to nx, and the other one was the exponential to a linear is 1 on a e to the linear. So that's what this is here. We have 1 on a e to the linear, and this is your 100x. Next one is x to a power and a function to a power. We also notice that this here seems to be a derivative of this bracket, because the derivative of this is 3x squared, and we could make that equal to 3x squared and divide by 3 like we've done out the front here, because they just cancel. And so we really have f and an f dash to an n. So if we look at the table here, an f dash f to the n is like this one in here, f dash f to the n, so we're going to apply that rule there. Okay, so here is f dash f to the n. Applying the rule, we have f to the n plus 1 divided by 1 on n plus 1. Next one is a power, but the problem with this one is that we don't have the f dash in this case. So normally we have to have f dash f to the n, but we don't have any f dash there, so we can't use that concept. We've actually got to expand it first and do it using the simple power integration. So expanding that using FOIL, we get first add as in as last. The pluses means you got separate terms, so first term, second term, third term. And now using the power rule, squared becomes a cube, but divide by the 3, and you can, same with the rest of them. But this one here, you can combine x to the 1, x to the half is x to the 3 on 2. So I still haven't integrated this yet. That's still the integral. We have integrated that one. We haven't integrated that. We have integrated that one. So now we've got to integrate this one, and so you raise it by 1, the power, so 3 on 2 plus 1 is 5 on 2, and you get the whole function there. Now you can get other questions other than these ones. These ones don't have any fractions, any divisions in the integral. If you go to the help sheet, of course, they do appear there. We've got here 1 on x, 1 on a linear function, and we have a derivative on a function. They all give lins, like that. Don't be confused with something like, say, 1 on x squared. That one can't be done using these lins, because it's not 1 on x, it's not 1 on a linear because you've got x squared, and it's not this one because the derivative isn't up the top. Derivative of that is 2x, there's no 2x up the top. So what you have to do is convert it into x to the minus 2, and then you can use the power, this one here, x to the minus 2, and you'll be able to use this integral. Okay, so one particular example would be something like the integral of 1 over square root x. First of all, you have to convert that to the integral of x to the minus a half. And then you use the power function on that. You're not going to use the ln rule with that because you don't have a derivative sitting up the top. Okay, next one here is kind of doing first principles of integrals, because we actually can't do the integral of ln x, but this is actually working it through the long way of getting the answer, the only way. First of all, they give us a hint. They say consider this and find the derivative. So this is a product rule between this one and this one. That's u and that's v. So we let u equal x and v equals ln x, so we can get the derivative of u dash and the derivative of v dash and put it into the product rule, and so we get ln x plus 1. So that's find the derivative. The next thing says hence find the integral of ln. I'll just change the setting out here. I'll just erase this and just do it another way. Nothing's wrong with it. Just give you another method. What you could do is say the integral of the left hand side, this is the left hand side, dy dx, equals the integral of the right hand side. So the integral of the left with respect to x equals the integral of the right with respect to x. Now if you integrate the left, that's just y. You can consider the dx as cancelling. And the integral of the right, we can actually separate that because it's separate terms there. That's the integral of ln x plus the integral of 1. And now y, we already know y because y is given to us up the top in the question here. It's x ln x. So we're going to put x ln x for y. So x ln x now equals the integral of all of this. And you can see that's exactly the next line over here. I've just swapped it around. X ln x, put on the right, that on the left, doesn't really matter. Use a different technique. And so now the whole purpose is to find, we want to find here the integral of ln. Now the integral of ln in this equation is this term. So obviously we can get that term over the other side and we've got it. Now the integral of 1 we can do, that's x plus the constant, and then we throw that over the other side. So it's x ln x minus x takes c, and so we've got it all down to the integral of ln x, just by rearranging the equation. So the concept was do the derivative first, and then do the integration of both sides. Okay, this one's the upper and lower sum question. We've got a quadratic, x squared plus 1, so it's curved, and we want four subdivisions, and we want to do the lower sum. Now the lower sum is these ones down here, that rectangle, that one, etc. That's the lower sum, and so they all have a width of 0.5 because we've got to divide 2 into divisions of 4, 2 divided by 4. And we're going to do f of 0, so it's that y times that width, that's f of 0. The next one is f of a half, which is that y value times by a half. Next one's f of 1, which is this y times a half, and then f of 1 1/2, which is f of 1 1/2 times by a half. Add all them together and that's the total area underneath the graph. To do the upper sum, we're going to use the dotted lines. Now notice the difference between the two. This starts off at f of 0 and ends up with f of 1 1/2, whereas this starts to the right at f of a half and ends up at the end at f of 2. The reason because to do the area of, do it in highlight, to do the area of this one, we actually got to start at f of a half and multiply backwards by a half. F of 1 times backwards a half, f of 1.5 times backwards, f of 2 times backwards by a half. Hence complete this statement here. The area underneath the graph has to be between two values, so it's got to be between the lower and the upper. Using technology, you can use fnint, and you should be able to get that exactly using the graphics calculator. Here is a graph of areas above and below. When you do the integral, you're really doing the vector analysis, so you can actually have negative areas when you're doing integral. At the moment, it says S is the area, so that's a positive and that's a positive. But when you do the integral from B to A, and notice it's the wrong way around, normally we go from A to B, left to right. It says why does S equal that integral? S being the area from A is going from A to B, but they swap it from B to A. To show that, let's actually put down what S is. Now S is the integral from A to B, but we've got to put a minus sign because that integral will give a negative value because it's underneath the x-axis. Because area is positive, we have to put a negative out the front, so negative times a negative is positive. Now if we do that integral, the integral of little f is capital F by definition, and so it's b to a, and then you have, now b to a is the negative of, the b on the top, a on the bottom is the negative a on the top, b on the bottom, right? So if you have a double negative, that will now turn into a positive. And so that, going back to the integral notation, a on the top, b on top. So I'm just proving that this is the same as this, going through the integration process. It does say explain, you could actually do that in terms of words. I've done it mathematically with a formal proof. Now if s equals t plus 2, so t plus 2, if that's equal to s, find the integral from a to c, so that's from the start to the end, that whole integral there. Now notice it's not just simply adding these two, because this s is negative and that's positive, there's a bit of a subtraction happening. To work it out exactly, doing it mathematically, we're going to do a to c. Now I can split that into two parts, a to b, b to c. Now we already know this bit here is minus s, because we know s is the area, which is positive, but this is a negative value, so it's minus s. From b to c we know it's t, that's the area. Now it tells us in the question c is t plus 2, so we can replace s by t plus 2, but you've got to be careful with the bracket, the minus goes in with the t and also in with the 2. So it's minus t minus 2 plus t. The t's cancel, so we've got minus t minus 2 plus t. These ones go, but you've still got a minus 2 left over. So the integral is minus 2 units squared. Now a conjecture question. Let's just sketch a curve of that one. You can put that in the graphics calculator and you'll get this function here. Explain how the curve could be rotated and generate a sphere, and explain why the volume of the sphere is given by this integral. So rotating about the x-axis, if we rotate it around, we'll generate a sphere. The area of a side view cross-section is given by pi y squared. So if we pretend that this is a cross-section view, right, you have to look side on, and like if you just take that piece there, right, after it's been revolved around, if you look side on to this piece, it would look like that and be a circle. Now the radius of that piece, that is the y value, so it's like this, y. So the area of that is pi r squared or pi y squared. So the area of a side view cross section is given by pi y squared. And the volume of a side view cross sectional disc is pi y squared times dx. So because this width here, we call that dx, a little width dx, we've just worked out the area is pi y squared, but we have to multiply that by a little bit of depth, right? And that depth there is dx. So the volume is area times by the depth, or pi r squared h, and so it is pi y squared times dx. That is the volume of a little slither of disk. So we've got pi y squared dx because that's y. Okay, so now if we want the volume, that's just one piece, that's just that one slice there. If we want the total volume, we have to integrate from the start to the finish of all those little discs. So it's a bit like getting that slice, then that slice, you know, all in doing the integral, going all the way through with lots of little divisions. So this here, the integral from -3 up to 3 of those individual discs is going to wipe out, sweep out the complete volume. Okay, so that there is explaining how the curve could be rotated to generate the volume. Verify the formula by comparing to the volume for a sphere. We know a sphere is 4/3 pi r cubed. The radius is 3, so we're expecting 113. If you put this into the calculator, you also get 113, so that verifies it. Now to develop the conjecture, we can say we're going from -a to a, because in conjecture we're talking about not just radius 3, but any radius of a. So we go from -a to a, pi times, now remember it was 9 because it was 3 squared, radius squared, so we got a squared, take x squared, etc. So that's our conjecture, if we're to generalise with letters. And generally the proofs go, do it for a number, do it for a letter, and then prove it with the letter. So we're proving now for the general case. So to prove it, that's the volume of the sphere. So 4/3 pi r cubed. So we're going to do, we're expecting to get that because we know the answer for a sphere is that, but we've got to do it with the integral first. So the integral, remember, was pi y squared dx. So it's pi y squared times dx, but we're going from -a to a instead of -3 to 3. Now we have to do the maths on this. So these are separate terms, so split it individually, integral of the first term, integral of the second term. Now the integral of the first term is just now done. So a squared, that's a constant, it's just a squared x. X squared, it's a power rule, add on 1 and divide by that new power. And then you're going from a, -a to a, so plug them in, plug in a first and then plug in -a and you get this. Do the same with this one. Combine like terms, so you've got all the cubes being joined, well that's 2a cubed and this together is 2/3. And then 2 take 2/3 is 4/3 because you can consider this to be 2 is really 6/3, 6/3 take 2/3 is 4/3. Pull the 4/3 out the front and we've actually proved that's actually the general volume formula for a sphere. Okay, so that's quite an advanced question there, but we need a conjecture question. So it's a good conjecture question to hit the SACE requirements in a test. 6, model train. We're given the acceleration and we have to show that the train's velocity is given by this. So if we integrate the acceleration, we'll get the velocity. And if we integrate velocity, we get distance. So doing the integral of acceleration, we just put down the acceleration function and integrate it. Now this is a division type question, so we're using from the help sheet the division integral. So what we're using is this case down here, which is the 1 on ax plus b is equal to the ln of ax plus b divided by 1 on a. I think I have written it as derivative on the function can be the ln of the function. If we go back and have a look, so I've written it here as there's the function on the bottom, and I've written the derivative of that is sitting on the top, 0.2. You can consider that as f. You can consider that as f dash on f, right? But probably be easier if you just consider it just a 1 on an ax plus b. Okay, so you don't have to put in the 0.2 and the 0.2, just consider that and just go straight to the ln divided by 1 on a. It'll be a lot easier. 1 on a times the ln of ax plus b. You don't have to consider it as an f dash on f, that's a long way of doing it. A bit silly. Okay, so now we've got the velocity, and that's the function there. And the next question was to show that train's velocity is given by that 5 ln, but the c is undetermined at the moment, and you can see it's not, they don't have a c just sitting there, they've actually worked out what c. So to get the c we have to use the initial condition. Now initially we're told it's stationary, so the velocity at time 0 has to be 0. So we put 0 for velocity, and for time we put 0. So if you put 0 in for t, that wipes that component out, and so you get ln 2 plus c. Times the 5 through, 5 ln 2 plus 5c. Take the 5 ln 2 over the other side to give minus 5 ln 2, and then divide by 5, so that's the c value. 5's cancel, so it's minus ln 2. Plugging it back into the original velocity equation here, we can put minus ln 2 where the c was. And combining this now to make it look like what we're trying to prove, when you have ln take a ln, it's the ln of the two divided. So like ln A take ln B is ln A on B, so that's the rule we use there. And we've now divided by 2, so 0.2 divided by 2 is 0.1, 2 divided by 2 is 1, and so that is what we're trying to get in here. That's what we're trying to prove. Next question, how far is a train travelled in the first 10 seconds? It's a how far, so that's working out a distance, so we have to integrate velocity to get the distance. So the integrate, to integrate that here, we're going to do the integral of this velocity function, 5 ln 0.1 t plus 1. And because we're not going to integrate ln, we don't know how to do that, but we don't need to because we can use fn into the graphics calculator. Now it does say in the first 10 seconds. Now this is okay if it doesn't change direction. Let's just see when it changes direction. Change direction when v is 0. So if you put 0 for v and solve for that, it's t equals 0. So since there's no other time, it never changes direction, we can quite easily do the integral from 0 to 10, because if it had changed direction, if this was velocity and this was time, then you would get something crossing the x-axis. Now if you did the integral of that, see it's possible if that was equal areas, if you did the integral of this from say 0 to 10, the integral would turn out to be 0, so the distance is 0, but that's just because it's gone right and turned around and come back. But it's asking for, that would be the displacement. It's not asking displacement, it's how far it's travelled, so that's a distance question, it's total. So it was important to work out where it changes direction, because if it changed direction at 5, we'd have to do the integral from 0 to 5 and get the answer, and then we do the integral from 5 to 10 and get another answer. This would be a negative value, we have to change it to a positive value, add it onto there to get the total distance. it's not that complicated because it's all in just one direction. So it's a bit like we got velocity and time and everything sitting above. So if we're going from 0 to 10, we're working the area underneath the velocity. The area underneath the velocity time is the distance. So it's from 0 to 10. There is a function, just put an fn int, and that's how many meters it's gone. Now the last one is electricity flow. Electricity uses more electricity. It's bought. When it's less, then it's sold. We've got the plot of the function of electricity here. And that's come from just putting that function into your graphics calculator. That's from 6 to 24, so from 6 to 24 hours. Now up to 6 it's 0, so it's along like this, and then it starts coming in. Now that's the time after midnight. First question, mark the graph with P to indicate the time when the household is buying electricity. So the rate of flow is positive, so that's coming into the house, so we're buying electricity then when it's positive, and we're buying electricity from 15th hour to the 24th hour in that region there. In between the 12th hour and the 15th hour, where the flow is going out of the house, so we're actually selling it back to the company. Okay, so part C, determine the number of units of electricity the household buys from the supplier over the course of the day. So we're going from 6 to 12, we're doing all the P section, 6 to 12 and 15 to 24. So doing those integrals on the graphics, you should get 16.09. Determine the change in the balance of the account by the end of the day. So first of all, let's work out how much is going out. So 12 to 15 we get a negative. That's the bit that we're selling to the electricity company. So we have to pay 16, we sell 0.35, and so the difference between that is 15.74. So that's the balance, and that they're units. Now the units, it says it's 17 cents per unit here. So that's the difference, or the balance, times 17 cents, so it's $2.70 that you pay. Determine the average number of units per hour. Now over 24 hours, we could have a formula here. The average energy is equal to the total energy divided by the total time, or the average energy times the time equals the total energy. Right? So therefore the average energy is equal to the total energy, 15.74. That's this balance, the total energy, divided by the time for a whole day, 24. And so in general, the average energy per hour for a whole day is 0.65 per hour that we buy. And yep, that's it.